Hi.
What's up?
I realized that problem we did last night that you see on my screen right now,
Yeah.
I did it the long way. By breaking this up into difference of squares and then breaking the difference of cubes up and the sum of cubes up, really was the, I eliminated about 4 steps by, instead of breaking this up into difference of squares, I immediately broke it up into difference of cubes. Notice what it is as difference of cubes. And
Okay.
this is being divided by cotangent squared x, which is the same as cosecant squared minus 1, which immediately cancels, and I have my answer in 1 step. In other words, this is a 2-step verify, and I think I did like 6 steps last night.
Okay.
It was only after I started thinking about it that I realized it was that. So what do you have tonight? Did you send me something new?
Yeah, it should be sending here soon.
Okay. We still doing verifying trig equations, or are we doing solving trig equations?
No, still the same verifying.
Okay. It must be getting hard, because they were
They're
starting.
like the same. They're like the same as last night.
Okay, because last night's were pretty hard, but what is real life is trying to solve trig equations. And you end up using an awful lot of the same techniques that you use to verify trig identities when you go to solve trig equations. And so all of this is really good practice for real-world problems where you have to replace a trig function with its identity in order to solve the equation.
All right, the first one sent.
Okay. Start with 1.
Yeah.
Secant x over secant x minus tan x has to equal secant squared x plus secant x tan x. Okay, I would say the left side is the more complicated side.
Yeah, I'd agree.
Let's see, everything's in secant and tangent. So, verify these pretty please. Okay. Let's see. If I were to multiply this by the conjugate, I would get secant squared minus tangent squared. What's that equal to?
1. Or
Yeah,
1.
it is. So that's not a bad way to start. Let's do that. Let's multiply by the conjugate. So in the top it gives me secant times secant plus tangent. And on the bottom, it gives me secant squared minus tangent squared, which is 1. Boom. Problem done. That certainly did not look like a one-step problem when I first looked at it.
Yeah.
In fact, I couldn't figure out how to do it.
Hard.
Yeah, it did. But sometimes, whenever you see something like this, it's always a good idea to investigate what would that be if I multiplied by the conjugate. And if it becomes one term instead of two, then it frequently is the way to go. This is sine cubed cosine squared equals sine cubed minus sine to the fifth. Some of these identities are just amazing. Okay, what are we going to do here? This one's pretty obvious what we should do.
Can we take sine to the third out from the right side?
No. Notice that we got sine, 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 cosine squared.
Turn that cosine into sine.
Okay. What is it?
Going to be
What's the original identity?
yeah, it's sine squared plus cosine squared
Equals?
equals 1.
So what does cosine squared equal?
1 minus sine squared.
Okay. And that multiplies together to give you that. Another one-step problem.
Yeah, the ones last night were really hard.
Yeah, they were harder than these are. Although these look hard.
Yeah.
But, gosh, one-step problems don't come around that often. Now, when you introduce a second variable, they can become tough, really tough. But so far, we've always dealt in one variable, and that's why I sometimes don't write it, because there's so many steps to these that I don't feel like writing theta 100 times. But if there's multiple variables, then you do have to write it. All right.
Yeah.
Let's see. The more complicated side is definitely the left. Addition is more complicated than multiplication. It's an interesting identity, is it not? That secant plus cosecant would be equal to secant times cosecant squared?
Yeah.
Okay. What relates secant to cosecant? Nothing.
Yeah.
If I use a Pythagorean identity, that relates to tangent squared, and that relates to cotangent squared. Well, if I could turn secant into cosecant, or cosecant into secant, I would do it. But I can't. But I can turn each of these easily into sines and cosines. So let's turn the left into sines and cosines. What do I have?
1 over cosine squared plus 1 over sine squared.
Add those two together.
Cosine, yeah, the denominator would be cosine squared, sine squared, and then the numerator would be just 1 plus 1. 2.
No, you're close. The numerator would be sine squared plus cosine squared. Correct? In other words, when you add two fractions, you have to find a common denominator, and then the upper left is sine squared, the upper right is cosine squared. All of that is 1. So that's the same as 1 over cosine squared sine squared, which is the same as secant squared cosecant squared.
Okay, yeah, I got it. That makes sense.
You get this step, that's the key step. You got to be able to add fractions with trig functions. In other words, this is sine squared over sine squared. This is cosine squared over cosine squared. Now I have my common denominator of cosine sine. Cosine squared sine squared. Okay? So, in fact, this was a two-step problem. Also a difficult one to solve, but only because, well, this one kind of uses the logic that if all else fails, convert to sine and cosine. If you can convert everything to sine and cosine easily and then manipulate it, that's not usually a bad way to go. In fact, the only time I don't go that way is if I could have converted secant to cosecant or cosecant to secant, I would have done that. But yeah, I couldn't do it easily. I'm not sure what the point of making these really complicated is. In other words, if the goal really is to just practice our identities, then all these other techniques really don't have much value. Is there anything after this? Am I getting the right side completely?
Yeah, that's right. Yeah, you're good.
Okay. We're in cosine and sine, okay?
Yeah.
So we certainly don't want to switch. If I multiply the right side, which is not the most complicated side, but actually it is. In other words, if you said which is the most complicated, I would say dividing by a two-term denominator is more complicated than dividing by a single-term denominator. So if I try to make the right look like the left, what's the first step I would do? What do you do when you see something like that?
Conjugate.
Yeah, always think that. So far, we've only seen one problem that did not involve that. We had one problem that looked like it was a conjugate and it turned out not to be. But in general, think this way when you see that. And the reason is that when you finish doing the denominator, you're going to have 1 minus cosine squared, which can be substituted by a single term sine squared. So the denominator is sine squared, which means the product of those two things must be that. And sure enough, it is. Exactly that. So in this case, I completely turn the right into the left with one step. This is interesting. It's showing me that there don't have to be a lot of steps for them to be hard. They can be hard even if they're one-step solutions. If I said do that division without even looking at the right side, what would you do? What can I use on the top to factor it? What is the top?
Sine cube, cosine cube.
Sum of cubes. So use the factoring for sum of cubes. What does the top factor into? First term is linear. Second term is quadratic. First term has the same sign. Second term has a minus sign on the middle term.
Sine plus cosine. And then sine squared minus sine cosine.
Uh-huh.
And then plus cosine squared.
Okay, well notice this is the bottom. So that's perfect because it totally cancels that with that. So that is our answer, or at least it's our step 2. Doesn't look like our answer, but that's because notice what I can do with that. The sine squared plus the cosine squared equals 1. So this becomes, in other words, everything in right here, that becomes 1 minus sine cosine, which is what they have on the right side. In other words, always be on the lookout for sine squared plus cosine squared, because then you can replace 2 terms with 1 number, and that's usually big.
It's pretty much just knowing your trig identities.
It's a little bit more than that. It's knowing your trig identities and obviously knowing your algebra, knowing sum of cubes, difference of cubes, sum of squares. I'm sorry, there is no sum of squares, but there's difference of squares. Now, after what I discover, what's the rest of this? That doesn't look like it's all it.
Cosecant squared x, cotangent squared x.
Times cotangent?
Yeah.
Squared x? Okay. Now, last night I would have started by saying that's the difference of squares. And I would have factored it into cosecant cubed of x minus cotangent cubed of x and so forth and so on. But after last night, I'm thinking the way to go is to factor this as difference of cubes, because it gets down immediately to squares and cortex. Guess, no, let's start with that. So if I assume that's difference of cubes, remember it's a linear factor and a quadratic factor. What's the linear factor going to be?
Cosecant minus cotangent.
Cosecant squared minus cotangent squared. Because remember, it's not a linear factor because it's to the 6th power. So the linear factor is actually squared. And the quadratic factor is actually a quartic.
So cosecant cube, or
to the
4.
fourth, because they have to multiply to give you cosecant to the sixth. And
plus cosecant cotangent.
both of them squared.
Yeah. And then plus cotangent to the fourth.
All right. Now, how in the world are we going to get what's on the right side from this? Wow. Cosecant and cotangent. What is cosecant squared minus cotangent squared equal to?
1.
Yeah. How does that help? Wow. Well, let's back up, because I don't know what to do with this. I don't have any clue as to how to turn that into that, even though this is just cosecants and cotangents, and this is just cosecants and cotangents. I still don't know what to do with that. I can't even factor that. That's not cosecant squared plus cotangent squared even. So, as sometimes happens, you got to back up and do it a different way. So this time I'm going to treat this as difference of squares, because I'm going to get cubics, but I can work with cubics. So as difference of squares, what is it?
Cosecant minus cotangent.
Cosecant to what power?
Squared.
Cubed. In other words, I'm going to treat this as difference of squares. Now, do you see what I'm doing?
Yeah, I see it now.
Okay. Different than treating it as difference of cubes. There's not very many functions that you can choose either way, but this is one of them where I can choose to either treat it as difference of cubes or difference of squares. Now, let's factor each of these. Now we really do have the difference of cubes. What is this?
That is cosecant to the third x.
No, after we factor it.
Oh, after we factor it?
Yeah, in other words, factor this. What's a cubed minus b cubed?
A minus b, a squared plus b squared.
Plus ab plus b squared. You got to know this because we've already looked at like 4 problems where you have to be able to do difference of cubes. So how does this factor, this term right here?
Cosecant minus cotangent, and then cosecant squared plus cosecant cotangent minus cotangent.
Always plus. The last term is always plus. Because it's multiplying, it just always is. And now let's factor sum of squares. Sum of squares factors how?
Sum of squares?
Sum of cubes, I'm sorry.
A plus b, and then a squared minus b, ab plus b squared.
Okay, so how does this factor? Cosecant plus cotangent
plus cotangent
times
cosecant squared minus cosecant cotangent plus cotangent squared.
I hope this is going to lead somewhere. What is cosecant squared plus cotangent squared equal to?
1. No, yeah, 1.
Okay, so I can cross that out and put a plus 1. And I can cross that out and put a plus 1. So now what do we have? We have cosecant minus cotangent times cosecant cotangent plus 1 times cosecant plus cotangent times 1 minus cosecant cotangent. Well, let's see. How is all of that equal to that? Let's see. Cosecant. If I multiply this times that, I get cosecant squared minus cotangent squared. That's 1. Right?
Yeah.
So I can cross both of those out, because multiplied together they're equal to 1. Now all I have to do is multiply that times that, and I should have what they're looking for. Well, that's cosecant cotangent minus cosecant squared cotangent squared minus cosecant cotangent minus cosecant cotangent. Cosecant cotangent, cosecant cotangent. What is it supposed to equal? 1 plus 3 of those squares. I made a mistake somewhere. Maybe not. Hold on, let me check my multiplication here. Cosecant minus cotangent times cosecant plus cotangent is going to be cosecant squared minus cotangent squared. That's equal to 1. So that was correct. Let me multiply my other two terms together again. All right. This times that is cosecant cotangent. That times this is minus cosecant squared cotangent squared. This times that is plus 1. I didn't do that correctly the first time. And then this times that is minus cosecant cotangent. So there's a cosecant cotangent minus a cosecant. Jackson, you still there?
Yeah, sorry, my connection cut out.
This looks like 1 minus cosecant squared cotangent squared. Now how is that equal to 1 plus 3 cosecant squared cotangent squared? So that's supposed to equal 1 plus 3 cosecant squared cotangent squared. You sure that there's nothing else on the end of that?
Yep, that's it. Oh, no, there is. It's cotangent squared x, but you wrote it down.
Right, I wrote it down right. Yeah, okay. Certainly isn't going to help to use the identity and put it in cotangent, because then I'm going to have a cotangent to the fourth. Wow. Well, the problem with these verifying is that if you make one math error along the way, you're never going to get to the answer, and furthermore, you don't know where you made your error. Treated this as difference of squares to get this. Then I did that as difference of cubes to get this. And then I did that as sum of cubes to get this. And then I took the ones out. So I had cosecant cotangent plus 1 times cosecant minus cotangent, and cosecant cotangent times 1 minus cosecant cotangent. And that times that, cosecant squared minus cotangent squared, which is 1. So it's this times that. And I've done that multiplication twice, come up with two different answers, but I believe this is the correct answer. And I don't think, if anything, this is proof that it is not an identity. Because notice that that means this would have to equal that, and that's physically impossible. That's like saying minus x squared y squared equals 3x squared y squared.
Yeah.
Well, that's like saying minus 1 equals 3. That's not possible. So, let's go on. I don't know what else to do and don't want to waste more of your time on that.
Next file.
Okay. Is that the last one, or is there another one to come?
I sent 2. Did you not get 2?
No, I did. That's the second one. I just didn't know whether I should close out my Gmail. GoToMeeting really taxes the system, and I like to close it out if I don't need it open. All right, sine squared of negative theta plus cosine squared of negative theta. Okay, what can I do with that? First of all, what's sine of negative theta equal to?
Negative sine squared theta.
So, since sine of negative theta is equal to negative sine theta, then this is negative sine theta times negative sine theta. That's what this expression means. What's cosine of negative theta equal to?
Negative cosine squared theta.
No. Cosine is an even function. It's equal to cosine theta
Oh.
because it's even. Remember, sine is odd, tangent's odd. Cosine is even. Wouldn't matter in this case, but that's the same thing as cosine squared of theta. Well, what's that equal to?
Sine squared theta.
Yeah, positive sine squared theta plus cosine squared theta. What's that equal to? 1. Okay. So let's do that same rationale. What's that going to be equal to?
Negative sine theta times negative sine theta.
Which is sine squared of theta. So when you're squaring it, it acts like an even function.
Yeah.
Minus cosine squared of theta. That's what that numerator becomes. All over what? Let's simplify the bottom.
Theta.
What is it?
Negative sine theta minus cosine theta.
Okay. Factor the top. Difference of perfect squares.
Sine plus, minus cosine, and then sine plus cosine.
How do we get sine? How do we get one of those things out of that?
I do not know.
Take a negative sign out. What's left behind?
So, yeah.
Okay. So this cancels with that, and I'm left with sine minus cosine over negative 1. What's that the same as? What's a minus b over negative 1 equal to? B minus a. A minus b is always equal to the negative of b minus a. So this that I have circled is equal to cosine minus sine. In other words, this is the a, this is the b. I'm going to turn them around. And that's what we're trying to prove, is that it's equal to cosine minus sine. Remember all those problems in algebra where you had this times this, and you were dividing it by x plus 3 and x minus 5, and you were multiplying it by x plus 3, and you were always able to do stuff like that?
Yeah.
Well, the only time you were able to cross out stuff that wasn't exactly the same was when you had x minus 3 over 3 minus x. We were still able to cross that out as long as we replaced it with a negative 1. So that's an important algebraic principle to remember, is that a minus b equals the negative of b minus a. Notice if I distribute that negative, I get a minus b. The parentheses are very important. It's not a minus b is not equal to minus b minus a. It's equal to the negative of parentheses b minus a.
Okay.
Now, we see this thing on the left that looks like, well, if I multiplied that by its conjugate, I'll end up with 1 minus cotan squared in the denominator. But that's not an identity. So that's not going to do me any good. I cannot replace that with a single term. So I don't want to do that. If I multiply by 1 minus tan, I end up with 1 minus tan squared in the numerator. That is also not an identity. So there's no point in doing that. So what should I do here?
Convert to sine and cosine.
I got tan over there, I got tan up there, I got cotan here. Can you convert the cotan to a tan?
You can.
Yes, you can. It's 1 over tan. Now I got everything in tan. That's got to be easier than converting everything to sine and cosine and going that way. But it's only easier if you know how to add these fractions. So add that together and tell me what the new denominator is. There's the numerator.
It's going to be tangent theta plus 1.
Now perform that operation. What do you get? You flip the denominator and multiply.
Yeah, I know. I'm doing it right now. One is I think a 1 plus tangent squared over tangent theta plus 1.
Flip the denominator and multiply. The tan theta plus 1 cancels.
Oh, yeah, that's right.
It doesn't hurt to look at what we're trying to prove. In other words, if you know that this has to be converted to tan theta, and they don't give you non-identities. The only problems they ever give you are identities. So don't always assume that it is an identity. In other words, somehow we have to turn this into tan theta. And if you know that, it avoids you making a mistake like you made. In other words, when I flip the denominator and multiply, the tan theta plus 1 cancels with that, and this tan theta ends up in the numerator, and that's all I got, is tan theta. So I could have solved it by switching everything to sine and cosine, but it would have been at least another step. In other words, then I would have had to deal with this new numerator that would look strange and a denominator that would look strange, and it would have definitely been one extra step if I had gone that route. So you don't always want to do that. First, look and see if the very first rule is to see if you can turn both sides of the equation into the same trig function. Notice that once I've converted that to 1 over tan theta, all I have is tan theta everywhere. And now it's just algebra. There's no more trig identities needed once you get the same trig function everywhere. Immediately when I see that, I think multiply by conjugate, but maybe not. Again, I would do the same thing on this part, multiply by conjugate. However, the left side is clearly the more complicated. But the right side, what can I turn that into immediately?
Sine and cosine.
Yeah, what? What is...
Well,
What is it?
1/2 sine theta. Or,
2 stays in the numerator. It's only the cosecant that turns into
okay.
1 over sine theta.
Okay.
Okay? Now I have everything in sines and cosines already. So, what if I try just adding these? That's going to work. What's the common denominator going to be? In other words, I can, in order to do anything with that, I got to multiply by a conjugate, which would also work. And it would work if I multiplied that by a conjugate. But I've got everything in sines and cosines. I don't need any more trig identities. I should be able to just add that to that. So what's the common denominator going to be?
1 plus cosine sine.
1 plus cosine theta in parentheses times sine theta. Always the product is the common denominator. What goes over on the left side? Numerator.
Hold on. The numerator will be it'll cancel, wouldn't it? Just be 1?
No. In other words, you have to figure out what do I have to multiply that by to get that common denominator.
Sine.
Sine over sine. I can only multiply by 1. So when I multiply by sine over sine, I get this in the denominator, and it leaves sine squared in the numerator. Okay, now over here, what does this have to be?
It'll be 1 plus cosine squared times 1 plus cosine squared.
Well,
So
it's 1 plus cosine quantity squared. Okay, which is 1 plus 2 cosine plus cosine squared. In other words, it's 1 plus cosine theta squared, which turns into this. Okay? Now, look for where we can reduce. In other words, let's go ahead and combine this. And rarely should you ever multiply these out. If you multiply them out, you will merely find yourself having to refactor it. What's the new numerator going to be? What can I simplify? It's going to be sine squared plus 1 plus 2 cosine plus cosine squared, right?
Yeah.
Okay, what's sine squared plus cosine squared equal to?
1.
So it really is 2 plus 2 cosine, right?
Yeah.
Aha. Now what can we do? Remember, we're constantly trying to reduce.
The cosine and the cosine cancel? I don't.
Well, not at this point they won't. But if you factor a 2 out of the numerator, what do you have behind?
It'd be 2 and then cosine.
1 plus cosine. That's going to cancel with this 1 plus cosine. In other words, now I can cancel that with that. I've got 2 over sine theta, which is the same thing as 2 times cosecant theta, which is what we're trying to prove. Oh, no, we were trying to prove that it was, yeah, it's 2 cosecant theta, yeah. Okay, so what did we learn from this? We learned that we don't always have to multiply by the conjugate. Sometimes In other words, when you have everything already in sines and cosines, then just proceed algebraically and everything will work out nicely. That's all I did here, was adding two fractions. Now, adding complicated fractions like this isn't easy, but it's not that hard. In other words, you really need to be able to do this. 1 over x plus 1 over y. Well, the common denominator is xy, but this has to be y. In other words, to get the common denominator, I got to multiply this by y over y, and I got to multiply this by x over x, right?
Yeah.
So that's really the way to look at it, is to do that, and then you end up with, well, that's y in the numerator, and this is x in the numerator over there. So 1 over x plus 1 over y goes to that. And make sure you can always add two fractions, no matter how complicated they are. These were complicated, but not that complicated. It's still just the common denominator is the product of this times this. And then figure out what has to go up there and what has to go there. All right. So you can see that this is a lot more than just trig identities. This is more algebra than it is trig identities.
Yeah.
And that's supposed to equal 1, okay? Well, let me think for a moment. I could separate this into two fractions. That fraction and that fraction. But that doesn't really look like it's going to do me much good. Tangent over this, yes, it actually would do some good. I'll tell you what, before we do that, I could change cotangent into tangent and then add those two fractions. But gosh, we got every trig function in the book here. So what's the best way to proceed?
Sines and cosines?
Yeah, we got 4 different trig functions here. No sines, no cosines. So let's just change everything into sines and cosines, because these don't interchange well. In other words, this turns into sine cosine, that turns into cosine sine, that turns into cosine, that turns into sine. So let's just go ahead and do that. So we got sine over cosine for the tangent, plus cosine over sine for the cotangent, all divided by 1 over cosine times 1 over sine. Okay, let's operate on the numerator. What's that equal to?
Sine squared plus cosine squared over cosine sine.
Good. About the denominator.
The denominator is going to be sine cosine over cosine sine. So.
Sine plus cosine over cosine sine. In other words, this is, excuse me, my mistake. They're being multiplied. It's just 1 over cosine sine. Right?
Yeah.
Okay. When you have a fraction divided by a fraction and the denominators are the same, well, if I flip that and multiply, It's the same as doing that. And that is the same as 1. So I really have 1 divided by 1, which is equal to 1, which is what we're trying to prove. What time did we start? 5:30?
Yeah.
Been an hour? That's how much fun these things are? As an hour goes by that fast. Let's do one more. Actually, I'm serious. I love these things. I know you're not finding them quite that fun, but what should I do here? This looks odd, but it's true. I've seen this identity many times. Whenever you see something like that, think what?
That'd be 1, wouldn't it?
No, but think multiply by the conjugate. Why? Because if I multiply by the conjugate, this turns in, excuse me, let's work with this side over here. If I multiply by the conjugate, the bottom turns into 1 minus sine squared, which is cosine squared. That's going to allow me to reduce a lot over here. I could also multiply by the conjugate here. We can work with the left side. Let's multiply by the conjugate, which is 1 plus sine squared over 1 plus sine squared. Turning the top into what?
1 minus sine...
Excuse me, I didn't mean to have a squared there.
1 minus sine squared.
Okay, which is the same as?
Cosine squared.
Okay, so that's what the top becomes. The bottom, always leave it unfactored, and this is the reason why. Because if I multiplied those together, it would be much harder to cancel. If I leave it in factored format, well, now I can do this. Well, that's what we're trying to prove, is exactly that. And I could have operated on the right side and multiplied by the conjugate 1 minus sine and turned it into the left side easy with one step also. I guess what I'm trying to get you to look at is why this is an automatic multiply by the conjugate. And the reason it is because it not only turns the numerator into 1 minus sine squared, which can be replaced by cosine squared, but we're looking at a cosine in the denominator. So I know I'm going to be able to make a real simplification by doing that. I'm going to end up with cosine squared in the numerator and a cosine in the denominator, and I'll be able to cancel, which I did, turning in the numerator into cosine. All right. I'll bet we're done with trig identities.
Yeah,
Well, we're not done with trig identities, but I would bet you our next session has more to do with solving trig equations than it does proving or verifying trig identities.
Are those harder or easier?
Probably easier. Probably easier. There's a couple of things you have to do to solve trig equations that you might not be used to doing. The number one thing is to think of them as algebraic equations.
Okay.
In other words, if I have sine squared plus sine minus 2 equals 0, that is a quadratic. And it factors into sine of x minus 2 times sine of x plus 1. And then I go from there. But if you first look at this, you don't see that. You see a trig equation. You don't see a quadratic. But you need to look, that's the secret of solving trig equations, is to treat them as quadratics. I mean as polynomials.
Okay.
All right. I will talk to you next time.
All right, thank you.
What is that? You have a session scheduled?
I don't think I have another one.
No, you don't have another one this week. Okay. Talk to you next time.
All right, thank you.
All right, Jackson. Bye-bye.